This is the second part of 6.3, and we're going to talk about the best approximation theorem, or BAT. The BAT simply states that the y hat we just found in the orthogonal decomposition theorem is the closest vector to y from vectors in W. So it says that y hat is the best approximation to y by vectors in W. So if you have to live in W, you're a vector and you have to live in W, but you want to be really close to y. Y is your like boyfriend or girlfriend, or yeah, whatever. So if you have to live in y and you want live in W and you want to be close to y, then you want to be y hat. Okay, every other vector in W is going to be farther away from y than y hat will be. All right, so that's the first thing it states, and it also states that the distance from y to W is the length of z, which we already knew, but this is just a proof of it. So this is y, the length of y minus y hat is what we're calling the length of z. That gives you the distance. All right, so I have a proof at the end, but we're just going to use it. And so we're still going to be using the orthogonal decomposition theorem, okay? It's just that now we know that y hat is closest to W, and we know the true distance from y to W is the length of z. All right, so here we go. Find the closest point in W, and W spanned by two vectors, to the vector y, and find the distance from y to W. All right, so the closest point in W will be y hat. Can we use the ODT? Well, that means we need to check, is u1 dot u2 equal to 0? Are they orthogonal? Well, yes, they are. We can see that readily just by visual inspection. All right, so what is y hat? Well, let's write down the formula. Y dot u1 dot u1 plus y dot u2 dot u2. Okay, y dot u1. So let's just go up here and look. 4 plus 2 is 6. u1 dot u1 is 2. So we'll have 3 u1s, because 6 over 2 is 3. And then plus y dot u2, which is negative 2, over u2 dot u2, which is 2. And that'll be times u2. So we're going to have 3 times u1, and u1 is 1 comma 1 comma 0 comma 0, minus u2, which is 0 0 1 1. And you notice I've switched again to linear notation just to save space, and I'm fine with you doing that in your work too. It would take up a whole lot of real estate if I was writing all my vectors like that, unless I were actually typing my answers, which I'm not. Okay, so this is the vector 3 3 negative 1 negative 1. So that's the closest vector in W to y. And then the distance from y to W is the length of z. So first of all, let's find z. Z is y minus y hat, which is 2 4 0 negative 2. Take away 3 3 negative 1 negative 1. And that's negative 1 1 1 negative 1. So the length of z is the square root of, square all those, square root of 4 is 2. Okay, a couple more problems, and then we'll call it quits. And I have some practice problems for you to do at home. And the solutions are on the last page for those two. Okay, find the distance from y to w, given that the closest point in y to w is y hat. So here, we're given y, u1, u2, and y hat. So someone's done some of the work for us. Someone has already found y hat. So there's extra information here that we don't need. We really don't need to know what u1 and u2 are because we're not finding y hat. That's been done for us. So this problem looks like it might require a lot of work, but it really doesn't. Find the distance. So we just need the length of z. So first of all, let's find z. Z is y minus y hat. So those are the only two vectors we need to complete this problem. Y is 3, negative 1, 1, 13. And y hat is negative 1, negative 5, negative 3, 9. Okay, so 3 minus a negative 1 is 4. Negative 1 plus 5 is 4. 4. 13 take away 9 is 4. So 4, 4, 4, 4. So the length of z is square root of 16 plus 16 plus 16 plus 16. So that's 4 times 16. I'm writing it like that because I'm lazy and I just want to be able to do this square root in my head. Square root of 4 is 2. Square root of 4 is 6. Square root of 16 is 4. 2 times 4 is 8. That's our distance. Okay, and last computation problem. This is a problem from your homework, and they're trying to confuse you with the way they have the vectors labeled. So this problem says find the best approximation to z by vectors of the form c1 v1 plus c2 v2. So what's happening here is vectors like this live in W, where W is the span of v1 and v2. And z is playing the role of what we called before y. So what really is being asked for is z hat. We want the projection of z onto w. And so the formula for that is z dot v1, v1 dot v1, v1, plus z dot v2, v2 dot v2, v2. So don't let the letters throw you off. All right, and so this is z dot v1 looks to be 6. v1 dot v1 is 4, 9. So 6 over 9 is 2/3 v1, and then I want to add on z dot v2 is 10 take away 8 take away 2. So that's 0, fortunately. And I don't care what v2 dot v2 is because I need to make sure it's not 0, which is not. So v2 dot v2, I'll just leave it like that, v2. So I want 2/3 v1, which is, so I'm doing this, I'm looking at v1 and I'm going to take 2/3 of that. So 4/3, comma, 0, comma, negative 2/3, comma, negative 4/3. And that's our answer. Okay. For quick true false, you might want to pause it and see how you do, and then come back and watch me finish them off. All right, number 1, the best approximation to y by elements of a subspace W is y minus y hat. So they're telling us that the best approximation is z. That's y minus y hat. And that's false, because we know that the best approximation is simply y hat, which is projection onto W of y. if y is in a subspace W, then the projection of y onto W is y itself. That's true. If y already lives in a subspace W, then of course the best approximation to y is y itself, because y is already living in W. Okay. 3, if z is orthogonal to u1 and u2, and W is the space spanned by those two vectors, then Z is in W perp. That's true. That's from a theorem we had, I don't know, back in either I think it was in 6.1, when we defined what W perp was, we saw that we only had to check that to see if a vector was in W perp, we only had to check it against the vectors that spanned W. All right, and the last one is true. This is simply the vector Z, and that lives in W perp. Okay, and that is it for 6.3. Do those practice computations and then check your answers.